Okay, so the idea today is basically we're going to go over exactly how neural networks work, exactly
Okay.
how they work.
Okay.
100% exactly how they work. Because most of the time, basically, everybody will explain to you how to do a forward pass to the neural network. That's basically the majority of what people will show you. They're like, this is a perceptron. This is how we do a forward pass. You know, this is how a perceptron works, just perceptron. Yeah, no, we're going to go backwards. We're going to do backwards, which is how neural networks are trained, which is the real, that's the thing that the majority of people who even use neural networks haven't done.
So it sounds like you're starting from a fully fledged state and working to understand the foundation.
No, I'm making an engine from scratch. I mean, I have the core engine written that's like 100 lines of code.
Okay.
It's just Python. Okay, so it's just Python. And then we can write the neural network live on the call.
Okay.
I think we could do it. I think we could do it. It shouldn't be too bad. Right, our brains, we have neural networks. This is kind of like not exactly what they look like in real life, but it's a fancy picture that kind of looks like what they look like. And you can see here in the, we got like a couple of the neurons very similar to the digital ones I'm working with today. Okay, and yeah, and this is basically when we're talking about activation functions later. This is basically what the inspiration came from. I don't know about this. I'm not a biologist really, but yeah, basically we have basically once it reaches the input level, reaches a certain threshold, it pops off and there's an activation. You can see actually this looks a lot different than the activation functions in neural networks. So it actually is quite different. It's really not the same thing at all. You can see in this diagram, there's like a pulse happening where in reality, there's sort of like we have they're often nonlinear, even though the most popular one now is ReLU, rectified linear unit, which is linear. But yeah, but this is where it's supposed to be based off of, more or less. This is what a neural network looks like. This is probably the best diagram I found. I think I stick this again later in the presentation because it's just such a good diagram. But this sort of explains everything, or this is the most explanatory single picture of a neural network I think that you can have. So on the far left side, we have x1, x2 here, right? You can see these are input values to the neural network, okay? So on one end, we literally just take numbers and just imagine for each one of these spots here. In fact, just this dot has actually two boxes here. So I'm going to call it boxes, but that's where we put numbers. This the easiest way to do computer science is putting numbers in boxes. So we have single boxes over here, actually, even though it's the same size as these double boxes. Don't be confused by it. So there's one input value here, two input value two, right? And then we have our z's, which get computed based off of the previous layer. And more or less, and I'm going to go into the details of this, but more or less we perform weighted sums, more or less, of these input values, and they go into these output values, these z values, and then we apply an activation function on that value, which is literally just some function that takes one input x and it has one output y. They're very simple functions, and they're just meant to have something change at some point, a noteworthy change similar to the the axon we were looking at before. So this happens all the way through the network. This happens multiple times. So we have input value go into here, it gets summed up, and then we have an activation function applied, and that's saved here. And then we perform the same thing again. This recursively happens all the way through the network until we get to our output here. Okay. And this final output at the end of the neural network, which there's only one output in this case, but there can be any number of outputs. There can be any number of inputs. And actually you can wire anything you want into this. And we're going to look at that. We're going to look at that today. So like you could stick a random function here if you wanted, but like you could literally stick anything you want here. You could stick a little plus here and multiply by 10. I don't know. There's no good reason probably to do that, but you can just think about this whole thing as composing together into a mathematical function, which takes these inputs on the left-hand side and results in outputs on the right-hand side. Okay. So basically the purpose of a neural network, what we're trying to do is we're trying to take some inputs and map them to some outputs. We're trying to create a thing, an abstract thing, which takes pairs of inputs. We have a whole bunch of different samples of data to where not just do we have x1 and x2, but we have, like, let's say 10,000 pairs of x1 and x2, or 1,000,000 pairs of x1 and x2. And we also have 1,000,000 pairs of what we expect the output value to be. That's what these true values are over here. So we have a million pairs of X1, X2, and a million sorry, not a million Ys, right? So a million outputs, since there's only one output here. But if we had,
What would be an example of it, like a use case? Like what is, like,
What are we trying to?
yeah, what are you trying to do here? Like what is, and I know I've seen these diagrams for LLMs and like, so that is trying to respond, trying to find the next words. But when you develop a neural network, is it for a very specific use case or is it more general purpose?
it's always for an extremely specific use
Okay.
case, basically.
Okay.
I'm not aware of any case where there is a general one. The most general thing now, and this is pretty fancy stuff, like up-to-date stuff, that I'm not going over really today at all. But with language models, for example, so anyway, okay. So first, I just want to answer your first question.
Yeah,
first, and then I'll get back.
yeah. This
Um,
kind of give context.
Yeah, yeah,
of,
no,
like,
it's
why?
Yeah. So the why is imagine we have some data and we don't know what function produces that data, but we wish that we could predict those data points. So I wish that if every time I had an X, I could predict the Y. Okay, any use case where you have that, where you have any type of inputs and any type of outputs. Perfect example is labeling cat images, right? So we want to know whether an image is a cat or not. Okay, it's just a 0 or a 1. Okay, and that's a perfect example because that would map to exactly this network, perhaps. On the left-hand side, though, we'll have an image. So instead of 2 inputs, we'd have a lot of inputs, all the pixels in the image, perhaps. And then on the right-hand side, we'd have a 0 or a 1 coming out of this end. A 0 means not a cat. 1 means cat. And then we can use this thing as a function just to check for cats. We can take any image. So what we do is we take the time to curate a data set of cats and not cats. Basically then we can take this data set and we can feed it in as input output pairs, and we can train the neural network so that when we feed in an image, it'll tell us whether or not it's a cat. And then we have a function which we can use. We just take that function and put it in a Python program, any kind of program, basically, and it'll produce the output. So it's basically, we're trying to, without understanding necessarily what's in the black box, that's exactly what it is. Neural networks are black box functions where you don't understand what's going on inside, but it works good enough. It's basically their approximations of some function that you're trying to, represent.
But in the end, it's like, you call it a function, but it's really a really long algebraic equation.
Yep.
Like, it's just like however many nodes and layers you have, strung together, adding together in some huge polynomial.
Yep, and we're going to go into the crazy into the details. This is just me giving a high level right now. So we'll get to that. And then, so in terms of like more general purpose usages, there are use cases where you use a neural network for a thing that you don't initially train it for. And the perfect use case for that actually is current LLMs. So current LLMs, they started using this terminology, and you'll hear it used to be back before 2022, it was only training. So there's only training. Okay, you train a neural network. Okay, now there's pre-training and then there's training. Okay, and the distinction between these two things is pre-training is them training on a data set, large corpuses of data on the internet. Okay, and again, it's a little complicated for this one, but I could totally do it in a later talk because people love LLMs. It's a pretty hot thing, so it's not any lack of interest in that. But it's just there's a lot of moving parts to the language models. So basically the pre-training is them basically just training to output text that it has seen on the internet. So we have this giant corpus of data and we just say, hey, given this text leading up to now, what do you think is going to follow this? That, predicting the next token, everyone says. Yep. That's the first step, is just doing that. And then the real training step, what they call the training step, is them doing alignment with labeled data done by experts. So people will sit down and produce input-output pairs of what they would like the chatbot to say. They use like Amazon Mechanical Turk workers to do this, to label the data. And then they take all this labeled data and then they take the model that they've already trained just to predict text. So the thing is, it predicts text, but it's kind of like a raw output, and it's not really something that's meant for users. If you use ChatGPT, that's not what you're getting. You're not getting the raw language model. But then the second step, the pre-training, is after they do the alignment, then it is like sort of like they take the knowledge that's already stored within it. So it is sort of general. Okay. That's what. So there are cases
for LLM, it's general.
Yeah, for an LLM, it's general. There's all this knowledge that's sort of buried inside there. And there's also lots of other examples with like diffusion models. You'll do like You'll take an existing diffusion model, which is really good, some stable diffusion that you don't want to pay to train or whatever. And then you'll put this little model on the side and like wire it into it a little bit. So you like take advantage of it without changing it and without updating those weights. And then so you can sort of steal, I don't know, they call it like transfer learning. There's different words for it depending on exactly how you do it. But there are ways to sort of steal information and make it sort of more of like a general purpose thing. But in general, it's very specific. Okay, so here's a perceptron. So how exactly does this work is a pretty important question. So these are inputs. Okay, so again, on this diagram, right, each of these lines that's pointing into one of these nodes, let's just say we're looking at this top blue node in the center here, just this top little blue node. That's what this guy is, the summation function here, right? We're taking all these inputs and we're taking weights.
It was a little laggy.
Okay, so we're taking all these inputs that are associated with weights and we multiply the inputs by the weight. Each one of the inputs by the weights, we multiply them and then we add it into a sum. We add them all together, basically. And you have this bias term as well. And basically, more or less, this is just like people would say you're doing a matrix multiply here. Again, x1 times w1. We just take that and then we do that for x2, w2, x3, w3. We multiply each of those pairs into sums or, into products of each of those values, and then we sum all those products together. And then after we sum all the products together, along with just a number, which is a bias term, we push it through an activation function, which again just takes one input and produces one output. They're very simple functions like sigmoid or rectified linear unit and stuff like that. And it results in an output, which is our prediction. And then we can determine how good a job we did by taking our prediction and subtracting it from what we expect the prediction to be. And if the number is larger, that's a large error. And if it's smaller, then it's a smaller error and we're happy. If the error is 0, the difference between y predicted and y expected is 0, then we're very happy. It's doing a perfect job. And here's Python code to implement one, because I don't want it to be abstract. There's no abstract math or anything. This is exact math showing examples with input values. So again, over here, we got x1 through xn. So in this picture here, we have x1 through x5, and then we have weights 1 through 5. And we literally z is often what's used to represent, you can see back in this, you see the z here on each of these nodes. That's to represent the pre-activation sum of products, right? So we sum all of these products together. We take a product x times w and we add it to z. And I initialize z as b here, but you could just add b separately as well. Yeah, so basically we just add up all the products of the input values times the weights. Bada bing, bada boom.
You're missing the activation. Oh.
No, look at that last line there. It's a rectified linear unit.
Okay, I see.
This is right. This is a ReLU.
Yeah.
So rectified linear unit, if anyone didn't know, is literally just like x, and then if it's less than 0, it's 0. So it's meant to be this, and then this, and then a line. It used to be that everyone would use sigmoid and like hypertan. I think those are the two common ones. Basically, the problem is, and this is sort of like the number, if you're actually practically training neural networks, almost all the considerations that you have, like all of the work, practically all of it, is all related to making sure that your numbers don't blow up to gigantic numbers. And it's going to happen today. I'm going to do it, and I'm going to run a network. I'm going to be like, oh, the numbers are too big, and it's going to say not a number or inf, and it's going to, probably, crash my program or produce some warnings and errors and stuff like that. It's a really common problem. We have problems with floating point precision. Which is obviously a really common problem in all types of computer science stuff in general. But in this case, because basically sigmoid function looks like this. I don't have a thing in here, but let's see if I can look it up. Oh, nice. You got the sigmoid, guys. Yeah, so this is what a sigmoid function looks like, this guy over here. Basically, when you get on this far side over here, up in this upper right-hand corner and the bottom left-hand corner, things sort of approach 0 and eventually does become 0, and basically you lose the gradient. And this is referred to as the vanishing gradient problem. It's a really common thing where you have a gradient and it basically disappears because of rounding error gets rid of it, and then you can't use that gradient. You can't follow the gradient to solve the problem, which is what we're trying to do. And a ReLU, for whatever reason, everyone says the ReLU fixes it. I still think it's a bit confusing. It seems to work well. The truth is there's a lot of this is alchemy. You're kind of like just experimenting with stuff. Almost all of the actual practical advice that you need help on, there's no help on the internet about it. And people just like literally the question, like how do I architect my neural network? Like how many neurons per layer, how many layers, what type of activations do I do between the layers? All this stuff is just sort of like, I don't know, try different things. Like literally just go ahead and go online, just gotta Google neural network, how to do architecture for this. And people, it's just hilarious.
But it's like, at some point, like your execution becomes more expensive the more nodes and layers in your network, right? So you just try to like minimize the number of those
and still get reasonable output.
Yeah,
exactly.
So like it'll finish in a reasonable time.
Yeah. So basically it makes it more expensive to train if the neural network's larger, although there are other benefits to what you're describing as well. So the other benefit is there's a common problem in neural networks where you can have what's called overfitting. And overfitting basically is where you, the term kind of is like it's self-describing a little bit, but basically you overfit the data, meaning that rather than describe the general function of what you're trying to represent, what it ends up doing is memorizing the data in input and output patterns. You know what I mean? Like let's say you have 1,000 different possible values, and it can have enough combinations to where it has 100 data storage places within this network, basically, where it's more or less able to hide 100 values in there. It could just copy your values from the input to the output, and then you give it a new value, which is supposed to be from one of those X's that is a similar type of thing, but it just produces garbage output because it's just memorized the data. It's not actually figuring out a general solution to the problem. So the other benefit for making it smaller is that you sort of force it to figure out a good way to solve the problem instead of a dumb way to solve the problem. Because there's probably
the bigger it is, the more it can memorize.
Yes, the bigger it is, the more it can just like do rote repetition, and it can just sort of replicate your output rather than learning what you want it to learn, which is a general representation of the thing you're solving.
So why is this a black box? We know the inputs, we know the algorithm, we can predict the outputs, like.
Okay, yeah, no, this is not a black box, just to be clear. So perceptron, not a black box.
Right.
I see what you're saying now. What's a black box is neural networks. Once you get outside of a few neurons, there will be descriptions. I'm going to have pictures later on where I'll show you a one-dimensional, like a one single parameter hill climb and gradient descent, and then multi-parameter. And you can see two parameters. You can see two parameters still because that's 3 dimensions, or it's 2 input parameters, 1 output parameter. It's a surface, right? I'll show it to you later. But once you get to a certain number, it just kind of gets hard to comprehend. And so the neural network as a whole is the black box. Lots and lots of these strapped together after we train them, that's the black box. So the question is what's happening when we're training? And when I describe it, then I think it'll be more clear.
Okay.
It's kind of like the vectors in, but the vector database and everything. It's literally thousands of points defining a thing in space. And each point is another dimension. You just, it's not, you can't picture it.
Yeah, there's an epic amount of effort put into trying to understand neural networks and stuff. And recently, both the two big Claude, Anthropic and OpenAI both sort of released things, and they were just saying, oh, we understand it a little bit. It's just like, no, you really don't. They made these separate models, which basically tried to correlate what they were saying with general features and stuff, and it was just kind of a joke. But anyways, so all right, so we need to know a little bit about calculus to do this. Okay, so Dylan, how much calculus have you done? I already asked everybody else.
Well, I have a degree in astrophysics.
Okay, my man knows calculus. Okay, so don't be offended. I'm going to go over finite differences today. Don't be mad. Okay, we still appreciate people who did it the hard way and plug in those identities into things and breaking it down for the professor. All right. So, but we're going to do it the easy way today. I'm going to talk, okay, we're not, I'm going to take a non-gatekeeping, like the opposite of gatekeeping approach to calculus and all of the math we're doing today. So basically, I just want to convince everyone that it's not that hard. The hard thing is learning all the symbols. You got to learn all the symbols and the terminology. And once you understand the terminology and the symbols and whatnot, it's oftentimes like, oh, why didn't you just say that? Is what it feels like once you finally get it. So it's just sort of like a little bit of like a lingo that you have to that you have to learn. So this is more or less a general description of the two operations of calculus that matter the most. It's basically the two operations in calculus. Everything else is just lots of complicated layers and doing this in multiple dimensions, doing this on different types of data. Basically, there's just like you can go really deep on it, but these are the two operations. On the top here, we have the slope. This is a derivative. If no one's taken a calculus class before, you know, rise over run in high school, that's what a derivative is. That's the first derivative. And then you can take a derivative, you can see how that changes over time. So if the slope is changing over time, you take the slope of the slope, that's the second derivative, so on and so forth. So yeah, it's just a rate of change. You know, we have lots of anyways, actually, I think I should just go to the next slide. Okay, yeah, rise or run, slope, bada bing, bada boom, is all different types of things, which all basically are derivatives. In fact, I think that math teachers should start saying derivative at the earliest age possible. That's what I would do. Because again, a lot of this is language confusion. So yeah, how fast is your internet going? Bits per second. I mean, this is a derivative. How fast is your car going? Every single time you look at the speed dial in your car, this is a derivative. How much you paid per hour, currency per time, literally anything that you can measure as a ratio that basically is some form of derivative or can be looked at in that way. And then here we have the slope formula. Seriously, it is just this. There's so much hemming and hawing about calculus, but it's just not that big a deal. It's a slope. So when we change the x value,
This kind of stuff I got.
yeah, exactly. So when we change the x value, we get the y value. The point, I want no one to be like, oh, I'm bad at math, I can't do it. Shut up. You can do math. Okay. You got to believe in yourself. All right. So, okay. So this is the definition of derivative. You lost yet? No. This is the definition of derivative, and it looks scary, but it's not that big a deal. Okay. Basically, this is is our slope here. So change in y over change in x. And it's called Leibniz notation. And over here, basically, we have our current f of x. So if we evaluate x at the current point, again, right, because every single time we're measuring the slope, it measures where we are. It matters where we are. If the slope is changing over time, where we are in the slope matters. So that's why we need to know where we're at. So f of x, and we can like sort of take the difference between f of x and f of x if we add a little bit to h. Okay, so again, we got just a function which takes one input and gives one output. Takes x, and we're just wiggling x around a little bit. We just say, hey, if I fiddle with x, what happens? If I increase x a little bit, what happens to the output of the function? How does it change? And if we divide by that same small change, then it is a slope. And if you think about it, it's the exact same thing as before, where in this case, we go back here, h is 3 in this drawing, right? So this bottom line here, h is 3, right? And we're just doing a slope, right? F of x plus 3 is this y1 on this, and f of x is just a y2 here. And we just bada bing, bada boom, that's the slope. Okay, so again, it looks scary, it's not a big deal. And the limit, basically limits are, I don't know, I guess some people do struggle with limits, but basically, it's never been a problem for me, like 0 has never been a problem for me. So I guess I don't know if I'm gonna be doing this justice today, but basically limits are as we're approaching a thing. It's the idea of a thing at some endpoint, and most of the time it's either some kind of constant, but usually it's infinite. It's usually infinity or it's 0. In this case, we're talking about the limit as it approaches 0. So we want to say, basically, we want to measure the slope, but this is a fixed slope, So in this picture, we have a fixed slope, but let's say the slope is changing. The question is,
Just go back one more. That's easy. Oh,
sorry, this one.
well,
The one
no,
with the
go
curve.
back some more,
Yeah.
yeah.
One more. There you go. Changing slope.
Okay, yes, you're right. Okay, yeah. So if we have the changing slope, then basically the question is, how can we get the most accurate possible slope if we're adding this small increment? This dx here is the h value, right? So well, how we get the most accurate answer is by making that smaller and smaller and smaller, and the closest we can possibly get it to 0 basically is the most accurate it could be. Without being exactly 0, because you can't divide by 0, right? So more or less, we just want this h to be really tiny. And if you make that h tiny enough, it's basically, you can do anything that you really need to do in terms of calculus, in terms of computing a derivative, doing integrals, all this stuff. You can do it just by actually calculating it. I mean, there's a whole, again, when you learn calculus, okay, just for context, I have never taken a calculus class. I've never taken a calculus class. I've never taken linear algebra. I took one intro statistics course, just one. So, And I taught myself this stuff. It's not that bad. I just had a guy tell me this a while back, tell me about the finite differences of my professor, and he was the man. And his name's Sam Samantha. He's still alive. Why am I saying like past tense? But yeah, so basically, you can literally compute it. And this actually shows you I really love this. Is the reason why I kept this. Is you see this at the bottom. This is the only finite difference approximation we will use in this course. This is an engineering course. So I do think it's really hilarious that there's like, people don't like if you do finite differences. But again, finite differences is literally we're literally just computing this instead of trying to solve this. Because when you take a calculus class, what you're doing is you analytically solve this and you basically break it down and you're able to solve for an exact number. And oftentimes, if the professor gives you these examples, it comes off to round numbers or, E or 1 or 5 or something like that, some perfect round numbers. But in real life with real measured data, which is at least half of engineering, you use measured values, and measured values are not going to be perfect. And there's no analytical solutions for most differential equations in real life. Astrophysics guy, correct me.
There's no what?
I know there's no analytical solutions for basically anything involving measured data in real life.
Right.
Yeah.
Yeah.
So so there's no analytical solution. So at the end of the day, if you're making engineering software and you're doing anything related to measurements and whatnot, you're doing finite differences anyways. So don't be afraid of it. Use it. If people don't like you using it, then whatever. Okay. All right. So yeah, so that was derivatives. Rate of change. Integrals. Integrals are basically sums, but when you have like analog, it's analog sums. That's how I describe it versus a discrete sum. A discrete sum, they'll use the E character. It looks like it kind of like a wacky E with like a zigzagging E. That's for discrete sums. Let's say I want to count apples, and we got 10 buckets of apples. And how many total apples do we have? We take all the apples in different buckets and we add them all together. That's a discrete sum. Integrals are the same exact thing basically, but we can break things down into continuous small pieces. Perfect examples of integrals, area, volume. I think oftentimes the way it's described is people say it's the area under the curve, but basically it's a sum. That's how I would look at it, is it's a sum of one or more values. So we can do area. This is in 2 dimensions. Volume is in 3 dimensions, but you can do any number of dimensions. So this is totally unnecessary and extra. I just felt like putting this in here just because I might as well, if I'm doing calculus, explain basics of calculus. It's just nothing to be worried about. Again, people make such a fuss about it, but it is not worth fussing about. So yeah, any kind of non-discrete measurement can be represented as a thing. Yeah, so like a perfect example of an integral, how much do you make per 3 months, right? How would you calculate this? If I need, how much would I make per 3 months? Well, if I have my salary, right, I could just take it, divide it by 12, and then multiply by 3. That's an integral. Literally anything you can take and break down into small pieces an integral. And here's some, I'm just showing area calculations before I move on to the next slide and show. And we don't need most of these. I mean, I guess I don't know if I'll ever need to compute the volume of a regular polyhedron in the rest of my life, but rectangle is helpful, and so square and triangle. If you have square and triangle, you're good to go probably. So here's an integral approximation, right? So this is like a very simple integral approximation to show how we could break a thing down into a smaller thing, right? So what we're trying to measure is the shape of this, the blue line on the left, the blue line on the right, black line on the bottom, and this red line, right? So we got it's a square. I was putting this in the ChatGPT earlier, and it kept on telling me that this was a pentagon, and I'm like, pentagons have 5 sides. I mean, I suppose that's the only regular shape that you could work into this by having a 0 length side, maybe, right? Or no, I mean, it does.
No,
Is that the angle that a pentagon makes between the red and, not the acute one, but the obtuse?
This one?
Yeah.
No. I didn't take an image. I didn't send it an image. I just asked it what a square plus a square with a triangle on the side, a square with a right triangle on the side. And it just kept on saying polygon. I'm just like, okay. I mean, 3 + 4 - 1 is 5 sides. I guess if it wasn't a right triangle.
Equilateral. Or not equilateral, but Not a right triangle, but
Exactly.
you
Yeah.
couldn't make a pentagon then.
With 5, exactly.
Right.
That's what it was doing, and I was like, anyways, I tried to say right triangle too, it couldn't get it, anyways. So yeah, so if we're doing a finite differences integral, we just do the exact same thing again. We're just freaking computing it. So in this case, we can take where we would normally do this. We're doing the exact same thing in this as we're doing in this. We're just break it up into smaller values. So in this case, we got a curve, and we can make it infinitely accurate by making our h value infinitely small. All we have to do is just make the h value smaller, 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 and it'll get more and more accurate. Until we, in this case, right, we got it broken up into 1 by 1 chunks, so they're very large, you know, very coarse. But in this one, we can break it up into super tiny chunks and add it together. Again, that's totally all extra. I just felt compelled to say calculus is no big deal. Teach it yourself. It's not a big deal. Also, there's so much math content online that is so good. It's like 3 blue, 1 brown is really good. I can't more highly recommend 3 blue, 1 brown. He's the man. But there's literally infinite math content online. Anything that students need to study for tests, there's an infinite amount of learning content online for. Okay, so now back to our neural network. What are we doing with time? Okay, 7:53. So, okay, back to the neural network. All right, so I'm gonna probably just come back to this as a reference, but all right, so now we're talking about backpropagation, right? So like, how does this actually work? How's the neural network actually do anything, right? It's, you know, we know how the feed forward works, right? We've already talked about that, but the question is, how do we go backward? How do we make the neural network get better at what it's doing, right? The question, you know, we initialize this with random numbers, which is basically what you do for neural networks. How does this thing get to a point where it actually can solve our problem?
So like all the weights and everything, they're like you start out with this random weights.
Completely random. Yeah. So yeah, basically random weights. Yeah. So yeah, random weights, totally random. So we initially like there's there's so much like alchemy, so much sorcery of just like fiddling around with stuff. I found that I made a thing to automatically tune hyperparameters. I love genetic algorithms. That was like the thing that got me into machine learning forever ago was genetic algorithms, which actually got me back into programming. Is the only reason I'm a programmer right now. But I use that to automatically sort of figure out what like basically it's another machine learning technique you can use. Maybe I'll do a talk on it for a later date. But basically you use Darwinian selection of programs, and you generate lots of programs, and you like reproduce the programs with other subprograms and stuff, and it makes and the ideas, and you call the bad ones, and the good ones you reproduce and stuff like that. And anyways, I was doing this for hyperparameter optimization, which is a thing that's done. It's not that weird. It's a pretty extra thing to do, but it's still a thing that people do. And I found that the most important hyperparameter, I said by far the most important hyperparameter was your random seed, which is hilarious.
Huh.
I said just setting a random seed number for your random number generator. Literally, that is the most important thing. I found they just reproduce, and it would change the network a little bit, and the seed would still be the same. It's like it's like the glorious golden seed. Just and again, it's another thing you just sort of pick randomly, but
It's magic bean.
yeah. The point here today is not to tell you how to be a pro at making neural networks, just to describe it to you so you can go fiddle with it yourself, and then you can figure that stuff out. Because I'm not an expert in data scientist. I'm just a guy who taught myself how to do this. I'm a programmer, not a data scientist, you know. So yeah, okay. So okay, so backpropagation. All right. So again, so we start on the left-hand side. Forward pass is computing all of our values all the way through the network, right? Using these perceptrons. We have a model of exactly what perceptron is. Each one of these circles here is a perceptron after the first layer, and we pass it all the way through to the output, and we get some output value. Okay. This is our prediction value. And then we put it into a loss function. Now, loss function, I don't know. When I name things by what they do instead of coming up with fancy or different or unique names for them. So I would call this the error function. And if everyone was in charge of the world, I'd say this is the error function because it's for some way of computing error, basically. For the most part, you're subtracting a y value that you know versus the y value that was output by your network. And again, the larger it is, the worse the network's doing, and the smaller it is, the better it's doing. I can totally send you this presentation after too. But a lot of times we modify it a little bit. So if you're if you're just trying to produce input-output data pairs, a really common thing is L2 normalization, which is just squaring the errors. So we sum the squared errors. So this is one example. We have one pair of input values, x1, x2, and one output value. But oftentimes you'll have a batch. You'll have a whole bunch of these different. So you'll have not just one pair, you'll have 20 pairs, 50 pairs, 100 pairs. And all these, the error values sort of get summed together. So that, again, so if for each one of these, we take all the errors and we sum them all together, and that's our loss function, which is sort of like a total error. It's like how I want to measure how good this did. And the reason why we do squared is so that we kind of like are saying, you know, the more wrong it is, you're really doing a bad job. Like if it's really, really wrong, that's a serious issue. And the way that we sort of emphasize how we want it to, you know, come down and also create really steep gradients for it to follow, which again, the gradient is just a derivative, just to be clear. So a slope. So we're trying to make a sharp slope so it'll creep down the slope. And actually, I think I have a picture of that right here. Yeah. So right, this is what we're doing when we're doing gradient descent. We start at some random point on the far left side here, and then as we iterate through it, we're able to walk down the gradient. So how do we walk down the gradient? Well, we just compute the slope at this point, right? So right here, we compute the slope, and then we can just say subtract the slope, and then it jumps a little ways. Now, this slope, you know, won't hold true for the whole thing. I mean, if it was purely a linear function, we could just say subtract slope all the way to the minimum, right? But we can't do that. We have to do it in small steps because, again, this is very high dimensional data. You know, this is just looking at one input value. There could be as many, you know, a big neural network right now is in the hundreds of billions of parameters, or like 80 billion, 100 billion plus. The big ones are 100 billion. It's 100 billion of these numbers, all that you're fiddling with all at the same time. It's just crazy to comprehend. So, okay, so how do we actually compute this, right? So back to derivatives, right? So we have our loss function, which we compute the error for. So we compute the error for loss function. We say you did this bad of a job, okay? So let's just say, I mean, I guess I'm gonna try to explain this in abstract terms to give an example. So let's say in sports, right? So I did individual sport. I did swimming was my main sport when I was a kid. That's an individual sport. Okay. So if I went and I swam and I did a bad job in that day and I didn't do it and I didn't do great, I had a high error. It was my fault, 100% my fault, basically. I mean, maybe you could say someone cheated or something like that, but basically they're edge cases. For the most part, it's totally my fault. Okay. Versus a team sport. Team sport, it's a lot harder to say whose fault it is. Exactly. You know, it could be this guy's fault. Maybe this guy did a really good job, so it's definitely not his fault, but this guy did a bad job. So it's more abstract. It's a little bit hard to understand whose fault it is. And then let's go even bigger. Let's say an army, right? So you got an army, and there's a general at the top, and he's maybe the most to blame. And then we got all these different guys underneath him, which are sort of his, you know, leaders underneath him as commanders or whatever. They all get a pretty large portion of blame each. And then everyone sort of gets less and less blame as it goes down. That is how I would say that's a good example maybe of how back propagation works. Okay, so at the end on the output, we have how much error there was total, what the total error was for this batch. Then if we go backwards though, we can go backwards through the network and say, okay, so this is our error, and also we know what the derivative of our error is. So we know not only our error, but we know how the error changes. So we know how to make it go in the opposite direction, again, by doing a subtraction of the oops. Just go back. So that's forward. But we can just go back. Sorry, I don't know where I'm going. The subtracting. Okay, I'll show the gradient descent formula actually. Okay, so again, this is us literally subtracting the gradient. So we've got current weight, and we want to subtract by basically something to do with our error. Our change in error with respect to the weight. So like when we fiddle with the weight, how does that change the error? This is the thing that we're trying to modify for all of the parameters in the entire net. A is sort of an arbitrary constant. This is a hyperparameter, one of the most important hyperparameters. And this one determines how big of a step we make. Again, in this picture, we have these steps, you know, there's a big leap here, but this might be too far. You know, this looks like it's no big deal on this example, but this, we could jump too far, like, because there could be just a little dip, but it goes up a bunch over here. It goes dip, and then it shoots up a bunch, and we jump too far. We can jump right over this little valley that we thought we were going to, and we're going up, and it's not good, right? We need to always be trying to go down. So that's why it's a really hard thing. The learning rate, if it's too high, you'll jump too fast. If it's too low, it'll take you a long time to slowly to solve your problem because it'll only be stepping small amounts. And it's sort of like there's a bit of a balancing act there to do that. Yeah.
So with each iteration, are you just changing one of the nodes weights at a time and then recalculating?
Good question. No, we're changing all of them.
So you change them all by the same amount?
No, they all have their own derivatives. So here's this shows that. So y here, right on the far end, this is our predicted y, right? And then over here we had our inputs. So the question, right? This is the blame game, like I was saying. Who screwed up? Okay, that's our derivative, and we just sort of pass it backwards. So the derivative here is the full derivative of the loss function on the far side. Okay, and then right, or this guy right here, right? Full derivative of the output, sort of.
So how do you have the derivative after just one output, the other depths?
These are all, the whole thing is differentiable. So we can analytically determine the derivative relationships between the output and all the other nodes.
Okay.
So that is the secret sauce of neural networks. You asking a good question. It's not a bad question.
Yeah.
To be clear. All right. Because the entire neural network is differentiable, which basically just means we can, determine its rate of change analytically ahead of time. But it's recursive application of the chain rule since you're a math guy. That's what we're doing.
No, yeah.
So we have the rate of change on the output, and then we can basically we can step backwards and determine this guy gets some portion of the blame. We pass back the rate of change of this. The question is, how does how does this change compared to how does this change? And the relationship between those two, as long as we encode that relationship. The thing is, again, I wrote an engine to do this automatically. It's like 100 lines of code. It's very derivative of, I'm using derivative in a different term, but of Andrej Karpathy's. Everybody knows who Andrej Karpathy is in machine learning. He's the freaking man. If you want to learn, he's tons of content on machine learning. That is the guy that I would suggest go watch the neural network 0 to hero. Down the 0 to hero. That's the good one. That one's really good. Anyway, so I made an engine to do this, the automatic differentiation stuff, and a whole neural network. And it's like 100 lines of code. So it's not a super complicated thing. It's just a matter of, again, you're just encoding what the relationship is. If I fiddle with this number, how does it change the output, basically? That's all you're doing. And as long as you're able to encode how that's done, we can take this one and say, well, how does this change? How does this change compared to how this change? And we can pass back the relationship to it.
How would you visualize that question though? Like, so what does it mean to be encoded? To have all of these different layers, the values, the differentials of all the different layers.
Mhm.
What does it mean to be encoded? What does it mean?
I guess I don't understand what you mean by encoded.
Well, you use the term encoded.
I'm sorry.
That's okay. So I'm just trying to understand how in the data structure you have the differential after it's past that layer. How do you go back and make that adjustment to the weight?
Oh. With this. Oh, you mean how, like, what are the relationships, you mean?
I think that's what I mean.
Okay.
Because like you have your differential at the end, you know what you should have gotten, you know what you did get.
Mhm.
So that's your overall differential. But for the middle stage or the first stage, how do you know what that differential, what the slope of that particular node is? Is that what you were saying you're able to do?
Yeah, so basically we start with the gradient on the output value on the error.
Yep.
And then we like sort of step backwards based off of relationships that we can encode. And I have all these relationships done, they're all right here.
So is it like doing the activation function backwards?
Yeah, everything is being done backwards. That's exactly what we're doing.
Okay.
That's
So
exactly
you're
what this code is for.
producing the different layers, the different values.
Yeah, so we evaluate it once and we get all the values and all the way to the output. And then
Okay,
we start with the loss function. That's our error. And then we say, oh, how do things change in response to this output?
okay.
Right? And we just pass back the error based off of these fixed relationships, which again, it just, you can.
I guess the thing is pass back is not like a mathematical operator.
Right.
Yep, yeah, no, I know, that's why I have passbacks right here, okay, so how do we pass back and add, right, right here at the top, okay? So we have our parent, right, is a parent node, so if we have a tree of nodes, right, that parent is the error. The error is daddy.
Okay, so error, when you say error, you're saying loss function,
Yes.
but loss function is a function or a value, like a number.
Loss function, it computes a value based off of your output and the expected output.
Right, but after one run, you've done one run and you have the output.
Yeah.
And you have the difference between the output and your expected value. To me, that sounds like a number.
Yep.
So why is,
The loss function generates that. Is that right?
No, that's what the loss function generates, it's just a number.
It's
All
a
it is
way
is
of
all it is a
calculating.
number.
so is it a number or a function? So the number is y prime minus, the function is y prime minus y.
So, okay, so there's different functions that are used as the loss function, okay?
Right.
So if we're doing, for example, if we're doing, I think they call it like cross entropy loss, or I'm trying to remember, but for us, for a single categorical output, if it's a 1 or a 0, there'll be a certain loss function that you use for that
Right.
that's designed to make it work better.
Yeah.
I'm just using it, I gave the example of an L2 norm because it's a very common way to normalize things in general. I'm used to L2 norm because I've been doing that with
So, but that's where you square the difference?
Yep, where you square the differences, and that
Okay.
produces a value, and we just sum all those squared differences. The sum
Yeah.
of the squared differences,
Okay.
that's our loss function that I'm talking about right now. There are a lot of different loss functions. You can make this
Okay,
whatever you
right,
want at the end of the day.
Okay, so you get so that's a number.
So that'd be like the loss. I mean, I don't know what the terminology is, but.
Yeah,
The error
Yeah.
makes
that'd be
sense.
loss. Okay, I guess
The
maybe,
result of the loss.
maybe the thing that I'm not
The
describing is when we're doing the gradient, the question is like, well, how do you have a slope? Is that what you're asking?
Well,
Yeah, how do you have a slope in
another
the
question.
middle
Yeah.
of the?
Okay, so what we do is we're in reverse mode auto differentiation. What we do is we just set the slope to 1 on the
But-
output.
Is it the slope of the neural network without the multi-layer perceptron, or is it the slope of the loss function?
That is just the slope of the output of the loss function.
So this is gonna be.
So keep going. The questions are good, guys.
But
This
the
is no
output of the
problem.
loss function is a scalar, and
Yep.
the slope of a scalar is 0.
Yes, I understand what you're saying, but
Like
the thing is,
compare the last-
we're doing reverse mode auto differentiation. I think that might, I don't even know how to do forward mode, because reverse mode is the only one that anyone does. But what we do in reverse mode auto differentiation is we assume a slope of 1 on the output. And it makes the math very simple if you assume a slope of 1 on the
Sure.
output. Okay, so we assume a slope of 1 on the output, and then all that we're doing is we're saying the relative relationships between, starting with the 1 on the output. So we just say it's 1. And then we can say, well, how does this relate to this? And how does this relate to this? And we can pass that back to determine proportionate blame, so we combine that 1 slope on the output with our actual constant value. And then we just say error, basically error times learning rate. You know what I mean? So
Not at all. Not at all.
Okay, all right.
So
Sorry, it can be, it's a little heady to describe. I
Yeah,
don't think
yeah.
I'm doing a good
Maybe,
job.
maybe your engine will, describe these steps.
Well, you're looking at one right now. So if
That's
this,
what I'm saying.
so this is, okay, so the question is, okay, so what's the relationship for addition for doing differentiation? If you're doing differentiation, you want to determine the slope. How does addition impact the slope? By a fixed amount. If our value is 1, what's the relationship to adding a 5? Well, it's 1x, whatever the value is. If that value is 5, then we'll change it by 5, right? The output. So that's a fixed amount, right? It's based off the output, okay? Now, subtraction. And then multiplication backward, right? So multiplication backward, if I have 2 values, A and B, actually, I suppose I could literally show examples of this, but we have A and B. If I fiddle with A, how does it change the output? If I double A, how does it change the output? It doubles it, right? So it's multiplicative, but it's multiplicative with the other value. So if I change A, if I double A, then it doubles the output, which would double B's gradient, right? and vice versa. This is the heady thing you have to get past. This is the hard thing for sure. This is like, we're going over right now, the hard thing. So, there's no need to, it's not a problem if you don't get it in 2 seconds. It would be very impressive if you did, probably.
And there's always two inputs. You always start with two inputs. Like in the diagram, it was
Yeah, generally speaking, when, in computer science in general, for the most part, whenever we have operations, we end up breaking them all into, so hypothetically, we break all operations into two input values and one output value. Even if you have a sum of a whole bunch of different things, oftentimes the tree representation of a program will be A plus an addition of B plus an addition of C plus an addition. So it's a whole bunch of different addition operations. We just break it up into pairs, more or less. Currying is different, right? Currying is taking a function and giving it one of the arguments ahead of time. It's sort of like binding an argument ahead of time.
Right.
Yeah.
Well, based on the idea that all operations can be broken down to.
You could,
Composed of-
yeah, you could look at a subtree as a curried function.
Yeah.
Like what I was describing there, a subtree could be a curried function. That basically was like a curried function. Because you've got a baked in value that's linked into the value, to the output. But again, okay, so, again, if the error changes, if there's any change in the error on the output, that will have a 1x effect on the change at the very output. I just want to make sure I do a good job. I'm trying to do a good job explaining this, guys. It's a really hard one, okay? On the output, right? So I'm here, I have the loss function. I compute the loss value, okay? If I change this, if I double the output value, how does it change? Well, it changes, 1x proportionate to the input. Linearly, it would change it by the same value that it increased by. And because we have that property, we can pass it backwards we set the derivative equal to 0 on the output. So that if the output changes by 1, then the derivative at the output will also change by 1, right? And then we can figure out going backwards. It took me a while to get this. And we can figure out by going backwards based off of what the relationship is between our output value and the previous input value. Literally what we do is we take the tree, like imagine we drew a tree of the neural network, right? So on the output, so here's the loss function, and then we got the whole neural network all the way down to the inputs at the bottom. Okay, so we're moving down this tree of values. Basically, we can determine, starting at the top, we can say, oh, hey, because if the output changes, we know what this is. Based off this relationship, we can say if this one changes by this much, it will change by this other quantity. If it changes by some, again, if it's a multiply relationship, then we know that it would be the output of B, and an addition operation would be changed by the output of A in a multiplicative manner. I'm doing a terrible job explaining this.
I don't think I understand.
Dude, it's totally cool not to understand this. Just so you know, I had to stare at
Yeah.
Karpathy's, I had to stare at it for a little, believe me.
So we're starting with like a matrix of ones and zeros.
Yeah.
That come from having a set of data in advance that we've decided how to represent in ones and zeros.
Yep.
Okay. And then filtering sand through a series of sieves, you've got these different transformations
That is a great way to describe it.
layered up. And we want to see the cat picture thing. We've
Yep.
got ones and zeros representing cat pictures.
Mhm.
At the end, we want just one or zero.
Yep.
And so we've already done this by hand
Mhm.
with our eyes, by labeling all the cat pictures. We know where the answers are for the training set.
For a training set, yeah.
So we take the data, put it through all the sieves.
We're not taking the dead. What we do is it's so confusing right now. So the values for going forward through the network are different from the values for going backward through the network.
Well, I'm back on going forward.
Okay, all right, no, that's fine.
Yeah.
Okay, that's
So,
totally fine.
so we get a 1 or a 0. We compare it with what we know about that cat picture.
Mhm.
And of course, you're gonna do this for all the cat pictures, all giant corpus, but
Yeah.
And so then we have a function that evaluates the output.
Yep.
For all the pictures.
Which is the secret sauce of the whole
And
thing is that the secret sauce of the whole thing is we can determine how good a job it has done, and that is all that we.
Right, and that's the loss function.
That is the loss function.
Okay. So that tells us,
It
Yeah.
gives you a score.
How close did we get to where we're trying to get?
Exactly.
Okay.
0 is perfect, high number is bad.
So if we ignore the bad propagation from it, but
Yep.
so then we do it all again? Or,
Yeah. I haven't got to
because
that
what
yet.
I need
I mean, we
is,
haven't got to multiple steps. We're just talking about one step.
because I think it's, I think it's the same.
But it's the same thing
We're asking,
repeatedly. So once
which
you
is
get this
that
step,
I
you're
have
good.
one value at the end though.
Yep, there's one value at the end.
What is the slope? I could,
The slope-
I thought we were doing it multiple times, comparing the errors, and the slope was the difference between the errors, and we
No.
want the errors to decrease.
So we
we're-
can do that. We can do the calculation multiple times. You can calculate a derivative by simply performing I mean, maybe I made it confusing by explaining finite differences before going and not doing finite differences. Although I think I do have a code example of using finite differences to compute derivatives, but we don't need to use finite differences. Okay, we know that if I change, okay, so if the value at the output changed, how would that change the loss value, right? If I double the value at the output, it would change it by.
But we only know that if we calculate it twice.
No, we
No,
don't. We don't need to
no, no,
calculate it
because,
twice.
so we have an output value, and if I double it, how do I know what the loss will do? You're saying I know what the loss will do?
You know what the loss will do, yeah.
Because
No,
the
if we
loss
double
is-
at the loss, we're talking, we're sort of like mincing words here at a certain point. There's the output of the loss function, and there's a whole bunch of stuff going on in the loss function.
Right.
Let's not worry about that.
But that's really.
Let's just assume the loss function is just gone and not worried about, and we
Yeah.
just have a number at the end. So
Yeah.
we have one number and then the neural network. If we start with that, it's simplest. I
Yeah.
don't have to explain the loss function 50 times. So it's just good or bad. It's just.
So I have one number and I have the
Yeah.
neural network, and if I,
So we-
you're saying if I double that number,
Then it doubles it.
if
What
I.
doubles what?
If I take that number and I multiply it by 2, then that number is multiplied by 2. So that's why it's a tautology. That's literally why you can set the derivative to 1, is because it's a tautology that if you double the output of the cost function, then obviously the output's a double. So that's why it's confusing.
X, Y equals X, Y.
The,
Yes, yes.
Okay,
so
I
the-
am following the math.
Okay, yeah.
the nodes are really just that equation
It's an
with a
expression tree.
random, but it's always the same expression with a random number.
It's always the same expression. The initial time you run it, the weights are random, but they're not random after that.
Right. Then you
They're
manipulate.
sort
the
of
weights.
pseudo-random, yeah,
Right.
after that. They slowly work their way into having some structure
Some,
after.
yeah, fitting.
Yep, into fitting it. And, okay, and, I guess I just want to make sure, okay. So. Okay, so. Let's just say we're trying to just do this, okay, just straight up hill climbing. Since no one's interacting, I'm just gonna walk up here, okay, so, so if we come here and we know the derivative, okay, we can compute the derivative because we do finite differences, let's just say, okay, let's say we can't do it analytically.
Well,
We
what
just-
function are we creating, finding do we know the derivative of?
This is the function. This is y and this is x.
Well, okay, so
I'm
this,
still.
But where's the
thinking.
second
We
value?
did it,
But
we
in
did
the
this whole
neural-
calculation one time.
Yep.
What's the thing that's changing that we can get the derivative of?
Again, the point is that nothing's changing.
well, because he said.
Nothing,
derivative
absolutely
is
nothing.
one.
I know it's confusing. The hard part about the reversible differentiation is getting this tautology that I'm trying to explain, which I'm doing a very terrible job explaining. It's not your, again, it's not your fault. Keep on hammering it at me. You guys be mean to me, okay? So, again, so if we change the output, right, it changes, obviously it changes in the same way that we change that output, right? If I change a number, if I double a number, it obviously doubles as a tautology, right? Okay, so that's 1. The slope there is 1. If we change it, then it changes the same way. Slope is 1.
The slope of this change that we're now applying to the result.
Wouldn't that initial change the slope? That, like you said, multiply by 2? Wouldn't that be? the
No, in
first-
this case, we'd be multiplying by 1, hypothetically. The hypothetical would be that we're multiplying by 1. We're still at the very output node. We haven't even stepped back in the neural network at all yet, right? And but
So, but we
this
need-
is the critical thing.
We need 2 points on that graph, right?
I don't
have
know
a
how to
slope.
explain it. You don't need 2 points. I'm doing a terrible job of it, but
I mean, so the 1 point we calculated, and then you're saying the second one is just like an arbitrary operation with doubling?
we can set the output to 1 and everything else is a proportion of how it changes. So maybe that's a better way to explain. Okay, so the output is 1, the output of the loss function.
We're now
Which
back
is
to
what we're
loss
trying to affect. All we care about is the loss function. We want to
Right.
make it do good, because right now it's doing bad. The error is really bad and we need to make it.
Right, so we already know what we want, right? We
know
already
what we want.
have the output.
We know
that
we want 0 on the output.
Yeah,
So that's, we're looking for 0. And so we know if we want it to approach 0, the slope is 1 on the output. we just say that because it makes everything else a proportion of that.
Yeah.
It's either double that or half that, or it's a small fraction of that.
So the second value is the slope is computed by the,
Yeah,
By the slope?
there's, we have values that are computed during the forward pass, which are the Z values, which are pre-activations, and then we have activated outputs. And then the third value, I suppose, would be the gradient. Also we have weights and biases, but in terms of the numbers that are changing every single time we run the network, the only numbers that are changing are the Z values, which are pre-activation, the output of the activations, and then the derivative itself, but that only happens during back propagation. Again, forward
But
is
aren't the
those
weights
two.
changing too?
The weights change after a full batch.
Yeah, okay, that's what I meant.
After we
Okay.
do a full batch, then we apply the
Yeah.
updates. The thing is, we already know if we had a thing that could determine which way to go down, like you guys get this. If we want this to go down, we follow the slope down. We say the
Yeah.
slope is 3x, and then we say, okay, well, I'm gonna subtract. I'm gonna subtract the amount to make me go down the opposite direction from 3x. So the slope is 3, I'm gonna subtract 3. So I know to go down, right? Slope is 3, subtract 3, subtract 2, subtract 1, subtract 0.5, right? So we can do it clearly. It's very easy to do with one parameter, right? It's a hill climbing algorithm. If it goes higher, we're doing better. If it goes lower, we're doing worse. We can compute the derivative, and then we know how to make it go down. Yeah, the hard thing for this one is getting it's a proportion. So we know if this is the best way to explain it, is the output, the loss function, the derivative of that, instead of knowing the actual derivative, we don't have a real computed derivative that we've gotten from calculated twice. We're never gonna have that, because we could do that. Absolutely, we could do that. You can train neural networks in different ways, and you can do finite differences. And there could be benefits to that. Like, for example, a benefit of using finite differences is that you can compute anything even if it's not technically differentiable. It just needs to have an output for that X value. So it can hack your way around non-differentiable things and just plug random crap.
Isn't the cat picture non-differentiable?
No, it's differentiable.
But it's ones and zeros. You're up. No, because your function is still continuous. Your output function is still continuous where.
No matter what, we take binary values and make them cast into
Yeah,
floats.
yeah.
So no matter what we shoot, the types is not a consideration for whether or not something's differentiable. It's just
Yeah, I get it.
literally is it differentiable.
I think it might be helpful to go back to the equation where we had the random value.
Mhm.
Because that's really all that matters.
Sorry,
Yeah,
the random value. What?
so,
You mean this
no,
one?
the function, the actual equation,
Oh, the update step.
The sigmoid with the sigma.
the sigmoid. Yeah.
Oh, you mean
You
the
didn't have this.
You mean the sigmoid?
Yes,
You didn't have the sigmoid, but you had a
No,
sigma.
this sigmoid?
no,
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 but the
no,
equation
the
that had a
equation,
The one with
sigma.
the thing that has an equal sign in it, the equation.
Okay, this has an equal sign.
No.
The
Before
percep-
I'll go back until we get to
No,
another
you're
equal
right,
The
sign.
right.
perception?
No.
Is
Yeah,
this, is this,
perceptron.
is this, oh, you want the perceptron? This?
That one, the one, two,
No,
Yeah.
with
That is the
with the equal
you
sign.
had,
There you go.
yeah.
This one has an
Yeah.
equal sign, sorry.
Right.
So I think that each one of those nodes,
Mhm.
perceptron,
Yep.
Yeah.
Neuron, perceptron, people call
Okay.
them both.
is that equation.
that's what's doing the
Absolutely,
work,
sir.
right?
100%.
Perceptron.
So,
Even though the activation function can differ, that sigma, the sigma thing here is an activation function. It can be different things,
But it'd
but
be the
everything
same
else is the
in
same.
every node.
Not necessarily. I'm telling, I'm
But
dead
it-
ass,
it
dude.
can
It's
be-
totally random. It could
But-
be, it's very complicated, how to build a neural network. There's things, for example, there's batch normalization is a perfect example. In the middle of your network, you normalize a whole layer. And the point of normalizing the whole layer is that hypothetically, if it learns something that has too strong of an impact on the network, because if you have a thing pop and it has a really large number, it can really impact the later layers. And the idea is that it makes it more stable for unknown values and stuff like that. So batch norm is a very common thing. People just stick in the middle of the freaking network. There is unlimited creative room for this, to be clear.
Okay.
This is just me describing, this is just the general description of how it works.
Again, I'm like way.
Dude, it's
behind
all
you.
good.
This graph.
I don't know if I'm gonna be able to do a whole.
Yeah,
no, probably not.
But I could do another one when I do it
So
later
good.
on, right?
So
Some
good.
other time.
This graph, the curve.
But this is great though.
Yeah.
Just two axes, one curve. This is the arrow ring.
Yep.
Again, my understanding was.
We
each
need
time
two
I run
values
it-
to have the
each
slope.
time
I
run
know.
it,
In
get a
fact, I
different-
made it so complicated by doing the finite
Each time I run it, I
difference.
get a different number.
Yeah.
which I'm hoping is approaching zero. I'm trying to figure out how quickly it's changing.
Not each time. We're not talking about, yeah, yes, this is what we're trying to do. I'm sorry, if you're
Is
just
that,
talking
is that
about.
right at
matching.
all?
Absolutely.
Yes.
Okay.
Yeah, no,
Absolutely. We're
But
doing,
then, so the 3D one with the manifold,
How many nodes are there?
because
The
the
entire
issue then is
thing.
that we don't have just two axes.
in a modern language model, it's like 80 billion to 100 something billion.
Okay.
Right, so we don't just have the two axes that we can change. We have-
This is two parameters. This looks really fancy, but this is two parameters. This
Okay.
is one neuron,
Okay,
to be clear.
so then we're still trying to go down.
Yep.
But the question is, if we did go down, even if we succeeded, we don't know why. Which exact,
I mean, would you know if you succeeded in this case? Do you know why?
well.
Do you need to know why?
And again-
That's the whole point of neural networks is we don't know
No,
why.
I know, but what I'm saying is like that, I'm trying to understand the back propagation.
Yeah, no, it's just, yeah.
But it seems like the question is, I'm picturing like a driving on the surface you showed a minute ago. the
Okay,
3D
yep.
surface. I'm trying to drive to the bottom of that.
Mhm.
But I've got like a separate joystick for each direction. You know, like one of those things where you have one that goes forward and one that goes to the side. But I have 20 of them.
Okay, yeah, it's a shifter, but with lots of them, is that what you're
Yeah.
saying?
Yeah.
A shifter with a lot of gears.
Well, like
Or what is
I,
the
I
shift?
can't go in different angles. And I
He's,
can't just let it roll.
yeah, he's just something, he's got, it's like a, whatever, you got a joystick for each direction.
Each
for each
direction.
Okay, so you're,
Each
okay,
axis,
this
each
is,
axis.
okay, so
Yeah.
imagine you're
We're-
standing at
we're
the
trying
spot.
to figure out,
You're
how
s-
did we get to this spot from that spot?
Yeah,
And, but we don't know which level.
well, you don't care how you got there. How you get there is irrelevant for sure.
But so what it looked like the back propagation was doing was trying to like guess.
Well,
Which, a change in which axis got us to where we are.
Absolutely, and it's doing it all at the same
No,
time. It's
no,
it's
no.
changing all of them.
But it knows how to change it. It's not.
It
saying-
knows, it's not
it's-
guessing. There's no guessing. Yeah, there's
So it's not
absolutely,
like you're looking at a second run and seeing.
Do we
trying to
guess
figure out
here?
Which,
no.
which
are
is
we
responsible
guessing?
for us
There's,
getting there.
there's no guess. We know which way to go down because
But-
we know what our slope is,
so-
assuming we know the slope.
With the
Again,
back propagation, how does the back propagation relate to the sigmoid? The equation that we,
Okay, yeah, so the equation, okay, so I could try to spell out every single operation, which that's totally doable.
just,
No.
I just want to see the very first step of you have the slope
Yeah.
between what you expect and what you got.
Mhm.
And
That's not what the slope is though. You just have, that's just your error function. That's just
The
your error
error
value.
The slope
Error
is between
value.
the error function last time and the error function this time?
We've only done one time. So we only have one time. We have our error. And we have some weird tautology statement that he makes, which I don't understand why he's making it.
No, okay,
I feel like you can explain this and just skip the tautology part.
no, you can't, because you have to set the gradient to 1. Everyone's asking what the slope is. And the only way I can describe it is by saying that we assume a slope of 1 because we know what the loss function, we know how we change the loss function, how that would change the output. If we could just reach in like God like we can't right now, but if we could just reach in and change that number, it would change it proportionately. How would that change
But now
in
you're
respect to
saying-
everything else in the network? It would change 1.
But now you're saying there's a relationship between the loss function value and the output value. And you're saying that they're like a one to
No,
one
we're-
linear relationship.
No, I'm not saying there's a 1-to-1 relationship. We have to
Yeah.
compute the gradient back through the loss function. To be clear, to be 100% clear, we must compute the gradient through the loss function, including all of the mathematical operations of the loss function, starting with our output value. But what I was trying to do is start with at the end of the network so we could start describing perceptrons, because otherwise we get lost in the
So-
sauce.
so we're
It's very
starting
easy
at-
to get lost.
We're going back to the output value and
Yeah.
we're calculating derivatives. Are we calculating derivatives of the perceptrons or the loss function?
We're calculating derivatives of all of the parameters that we want to fiddle with. That's what we care about. But the thing is that we also compute a whole bunch of derivatives that we don't care about in the service of computing the ones that we do care about. So we end up computing all the things. So imagine we have a giant tree.
Yeah.
We need to compute gradient for the entire tree. Every single node, we compute how its slope is. And we do it all based off of the end. Again, it's
Yes.
this is why it's called reverse mode auto differentiation.
Okay, so the top of the node is the output.
Yeah, because we're going in reverse.
And then the next node is the second, whatever, the last layer of the neural network.
Yep.
So the loss function is not involved in it.
It absolutely is involved. No, it totally is involved. The loss function is what computes the output value, and the output value is the thing that we're fiddling. So at the end of the day, we have to compute the gradient all the way backwards.
loss function is the actual value that we care about.
No, it's not, it's the error.
It's just to check how far, like.
The
how
loss function
accurate it is.
the loss function is sort of like an abstract thing.
Right.
Any function which can compute a value, which if that value goes to 0, you're happy with the output.
Right, right.
That's basically the way I think about it.
Yeah.
That's the abstract way.
So it's like an accuracy measure.
It's exactly what it is.
Yeah.
100%.
But how, so what value do you feed in your backward propagation? What do you start with?
So you start with 1. And again, the entire point of starting with 1 is so that all the other changes are relative to the output. Meaning that one is, let's say we scale
Like,
anything
you
on any
multiply
scale.
times 1, if you divide it, like, it's, 1 doesn't get you any. What are you, what is the variable with it that is passed in the back propagation?
There's no variable. It is just the 1. So we start with 1, but it becomes not 1 almost instantly. Again, so what we want to know is every single one of the parameters in the whole thing. We want to know if I change this parameter, how does it change the output of the loss function at the very end, our total loss? I'm gonna call it total loss from now on. That's a number, scalar on the output of the loss. Okay, so if this, we want to know how does this number change if I fiddle with this dial over here and we have a billion dials.
Got it.
Basically, we can all determine that all proportionately based off of the output, right? So any given thing, let's say I want to scale any given thing at all. I can scale any given thing compared to any other thing. We can always compare two things. If I say how many, I don't know, miles per hour is a common speed calculation, right? But you can come up with inches per 3 hours or any other thing, right? We could calibrate to that and divide it into that. And then we could always use that, ratios are a perfect example of this, a ratio of a thing where one is some known quantity and then everything else is just compared in relation to that one being 100% oftentimes, but it could be anything. So more or less that's what we're doing here when we set the gradient to 1 is that we're setting it where we want to know what all the changes are in relation to this. And since we know how to encode a relationship of that node and the previous node, and again, there's not one step or two steps, there's a million steps backwards. And each one of those changes has a relationship which is encoded based off of what the expression tree is. So the expression tree, if it's a plus, we know how we change how these gradients change this output based off of the fact that it's plus. And so starting with the tautology of setting it to 1, it's really just setting it to a ratio that starts with 1. So the output is 1, and then everything else is comparable to this output number of 1 because we're encoding it based off of relationships. So we only need the 1 because everything else is based off of the 1. Everything else flows down from the 1.
Right, so start with the next level of the tree. So the top of the tree.
I should have put down I should have got a diagram of this, but no one has it on the internet.
Well,
Oh,
nobody has it on the internet.
yeah, no one has it on the internet.
Because what's confusing to me is that it sounds like you're not changing anything. You have a constant.
We haven't changed anything yet.
Well, but I mean, in the back propagation is a constant, and I don't, from one run to another, what actually changes in the back propagation?
What changes is these derivatives are based off of what our input values are. So, like I was showing before, okay, what am I looking for?
Can we go back to that diagram?
So actually, wait, let's go to the, right, so, yeah, we can go back to what diagram?
The flow chart.
Oh, chart. Oh,
That.
this one.
The one with weight 1 and weight 2.
The square boxes.
That guy.
This guy.
Is this not helpful to the conversation?
Oh, it totally is, yeah. But this is not correct, though. The thing is, you guys want an exact calculation. I'm trying to give you an exact calculation. This is not, it's not.
We're not trying to get
Yeah.
this, like, the concept and what conceptual values are passed back. So
You have the derivatives of everything. You have the derivative of the loss function and the derivative of each perceptron.
Mhm.
And so you put in a 1 to the equation that's the derivative of your loss. Right? Is that where you put in the 1? And then you.
Yep.
get an error, which is DE.
Yep.
And then you put that in and you just step back through.
Yeah, so,
I see.
right, so it's a
Okay.
one here, but the thing is that the
Yeah.
loss function is itself, you know, it's an algebraic expression.
Yeah,
All this stuff
okay.
is broke, the whole thing, starting with this is daddy at the very top, and
Yeah.
then everything else is descendants. The loss function is all in here too, right? So we have to compute the gradients of everything in the loss function, it's an
Yeah.
algebraic expression,
Yeah.
so we start with that, and then we go back to every value which is dependent on this. Every single value which is dependent on this, we step backwards to each of them. And again, we have a tree in memory of this. That's what this engine that I was gonna show does. It has a tree in memory of the entire algebraic expression.
Okay, so you are storing a value of what it is at each node.
The perceptrons.
We literally have a box for every single one
Yeah.
when we're going backwards, and that box is the derivative.
That I
It's all
think
based off of the one.
All right.
Every single one, we move back one step and we say, now it's this because this is an addition operation. So if this one. we
You
put a-
have more than just the final output, you have all of the outputs.
Yeah, you have all of, in terms of things that change on every iteration, your X values can change. Your, you know, all of the values of the perceptron itself, right? So all the input values all change.
So you end up.
Because you're running it with different data. You don't run it with the same exact data every time, so those all change. And then when those numbers change, that changes the derivatives. So again, part of the derivative is a fixed relationship, which is what I encoded and I was showing you there. That's part of it's fixed, but the part that's not fixed is the numbers which are in this relationship, because the derivative is not constant across the whole thing.
So after you're done back propagating, you have now a network of errors for each node, basically.
We have a network of proportions of error each of them could possibly be assigned. So we
Okay.
know how bad a job each node did.
So
you're
the ones
comparing-
closest to zero,
Go ahead and ask.
Oh, so you're
that
comparing
makes sense.
how close each one of those outputs of all the nodes are to our prediction?
No, we only compare the final one.
So if you go back to
So
the,
there's only one
So
final
we can,
output.
we have only one final output. Oh, even though you can have I mean,
but go back
generally
to the,
speaking, the output of the loss function is a single value. So yes.
so go back to the manifold. So you have the point where you start with, where the dot is.
Yep.
And you have basically the slope in every direction. Because when you back propagate, you calculate the errors of every node, and that
Yeah.
gives you the slope in every direction. So you know the ones closest to zero are shallow and flat, and the ones closest to -1 are the directions you want to go.
So it's like a map.
Yeah,
Kind of.
It absolutely is. We're doing
Yeah.
exactly what this thing is. That black line is what we're doing. We're trying to follow it down into
Yeah.
the lowest point. We're trying to do it. Sorry, man. I'm doing a terrible job.
the ones closest to 1 are the ones you want to avoid, because that's getting you to greater error.
Yeah, and this
And-
looks beautiful and nice and simple, but a lot of times it's not this simple. It's really hairy. And again, you were talking about earlier, it's not just 2 dimensions. There's a
Yeah.
ton of dimensions. The question is, am I really walking in the right direction?
Yeah.
But the thing is that we have to guide us the proportionate error. We know how good or bad a job each
Yeah.
node did proportionately to the output,
Yeah,
with the output being 1 and everything else is defined in relation to it as a proportion of that error. And then we can take that error value, okay? So a change in error over change in X, which is just, 1 or whatever, and we can multiply by the learning rate. So we can take the weight and we can subtract the learning rate times how bad a job it did for each node. And that's how we update a node. This is just how we update a single weight of one
Yeah.
one
How
parameter.
does the derivative of error change from one node to the next? Does it?
The derivative that we're passing through, which is the derivative of the error, right? It's the derivative of the error with respect to a given weight or a given
Yep,
part of
yep,
the algebraic expression. It changes the whole way through, based off of each of the different ones. So each of the ones has done a better or worse
Oh,
job.
New,
but-
wait, so this is what's passed on as the next. No,
Yep,
no,
that's the
this
next
is-
way,
this is-
yeah.
this- No, never mind, I got it, I broke. But how do we know the error rate at each node?
How we know the error rate at each node is because there are rules that are fixed relationships in calculus. That's what I was showing earlier. So the product rule is an example, right? So if we change either of 2 inputs of an output value, which are being multiplied together, then they, like, if I fiddle with this one, if I double this one, then it'll double the output, which means that the derivative of this with respect, derivative of this with respect to this is like, it's hard.
So it's a-
It's hard to
it's a
explain. It's hard to
relationship.
explain these bidirectional relationships. It's like this. That's why it's hard to, it's hard to put in words, but I have it coded right here. If we, if we change one of the values, then it will double. In fact, I can calculate exact derivatives. One second. I think that I have code for it. I think it's in. Okay, yeah, so, okay, so we can just, calculate the derivative at any given point or whatever. And so okay, just to be clear, this right here, this function right here, this is like a secret decoder ring for all derivatives you could ever want to calculate, basically. I mean, this doesn't take vector valued functions. So for example, if we wanted to compute the Jacobian for math guy, if we wanted to compute the Jacobian, we want to do vector valued functions and stuff. It's a very straightforward upgrade to this. We just add another dimension, and that's all that we're doing. But basically what this will do is this says, give me my derivative of each of my input values with respect to the output. And the way that we do it is by, this is just finite differences. So I set my H value to some really, really tiny number. Again, that's our X that we're changing the function by, right? Right, this H value, I'm just making it super duper duper small, and it'll be correct. And I just take the output. So again, this is their derivative definition. So the derivative definition, right? F of X plus H minus F of X over H. This is F of X plus H, the modified args, minus unmodified result, right, which we've already calculated ahead of time, F of args. And then that lets us calculate the partial derivative of this, because we also divide it by H, sorry, down on here on the end. So this is the finite differences formula right here. Calculating the output with respect to the input, and then I just append it to this partial, I append the partial derivative, and to the total derivative is like a description of all the possible input values that you have. So a total derivative of any function is basically description of partial derivatives for each one of the input values. So if I fiddle with X, how does that change? If I fiddle with A, how does that change output? If I fiddle with B, how does it change the output? If I fiddle with C, So a total description requires you to have all those, and that's what this computes.
What is F? What is the content of F?
F is, sorry, it's a function.
Yes, but is that
So down here,
network dependent?
So down here, I made like this little decorator to wrap this up and do some, just to do some fancy business. But basically, F is add here.
Okay.
So F is add, and add has two arguments.
Yep.
And basically, I'm able to create this function and just pass it into this. Again, I could just draw, I made this decorator here, but this decorator is just to make it so I can print out derivatives and it's convenient to show people.
Yeah.
But you literally can define your own function without this decorator and then just pass this into diff as the function. So the first argument is add, and the rest of the argument is whatever your args are, some arbitrary number of arguments. And then we have this, this H value we're passing in. And yeah, it'll use that function. So that goes down here and it actually applies the function, right? So we pass an add, it tries add with just 5 and 4 here, right? So it does add with 5 and 4. And then we create a modified version of the arguments, right? Again, this is a little more complicated because I'm doing multiple, the full derivative, but it's a little simpler if you do just the one. But so our modified args is just exactly what our args are. And then I just take the one arg that I'm looking at right now. I want to know the current parameter that I'm looking at, right? Because I'm going over all the args. So for each one of these args. So for this current arg that I'm looking at, if I fiddle with the input value for this arg, right? Then how does it change the output? Which is this partial derivative that we have here. And we're just appending these onto the full derivative, and then we return the full derivative on the output. So I can show you. And what this is, just so we're clear, these like 3 right here are the only derivatives you need to do like an entire neural network, basically. You just need these and like ReLU, I think. But sorry, what?
How do you know which to use?
How do you know which? You mean sorry, what?
So you have these 3 to choose from.
Yeah. So this is just me I'm just showing, this is me like sort of displaying that this can differentiate things. So I'm showing under the operation of addition. This is a very general thing that I'm calculating here. Under the operation of addition in general in Python, if I add two numbers together, what is the full derivative of this function at these given points? Again, we can only calculate the slope at a particular point in space, which is why we have to pass in these values. And in this decorator, all these guys are 5 and 4 here are A and B. I'm just passing them in as A and B, and I just made this decorator could, to show how great I am at Python. So, even though decorators are probably one of the most confusing parts of Python, really, I really didn't like them for the longest time. I finally got over it, but yeah.
Are you using the derivative here as a sort of signature that every function basically to sort of run the functions backward?
Exactly. Well, again, basically, if we could start with one, again, if we start with one on the output and we know how one node, the parent node, relates to its children, and then we know how each of those children as a parent node relate to each of their children, which again, that relationship is fixed as long as it's the same operation. If I'm adding two things,
Right. So
and on the output,
that's
it's
what
the
you were
same
just
thing as
doing.
it's the same thing as the next layer up adding, and the same thing as the next layer up adding, which is why we only need to figure out all of our fundamental relationships, which is only a handful.
The derivative is defining that relationship between the parent and the child.
The rules for how derivatives work, so these product rule, quotient rule, these type of things, addition rule, these are, the thing is you could experimentally determine these very easily. That's why it's nice to have the magical decoder ring. I don't know why.
So if you showed the sigma equation that we
Yep.
showed before, the perceptron, like you could, like, this is what you're taking the derivative of, no?
We're doing the derivative of all this stuff, but the thing that's most common in the network is this.
Well,
for
yeah.
sure.
Yeah.
This is the vast majority of the network.
Right.
I mean, it's
And
different
so-
for language models, but
You're not using calculus rules to take this derivative, you're just using the finite different, whatever you call it, finite.
Nope. Right now I'm doing finite differences. I was
Yeah.
just showing you finite differences
Okay,
because it's an easy way to calculate these things and to show what the relationships
yeah,
are.
okay.
All I'm trying to do is just look at relationships right
actual-
now. That's what I was
Are
trying
you
to do.
saying actual neural networks use calculus rules to do these derivatives? Because I guess you could.
No. My neural network engine that I made is using real calculus rules right now. It's using them. I'm not
Yeah.
doing finite differences.
Yeah.
I'm
okay,
just, this is
okay.
just the finite differences thing here is just a little, this
Yeah.
is like a little example test bench to show people how to compute any derivative. That's all that this is for. This is not, the true thing is on the left-hand side here. This is using real calculus. These are real calculus rules.
So we have a set of transformations to our initial matrix.
Starting with our known
numbers,
top.
right? And there is math that tells us,
Which you could experimentally determine using this finite differences thing very easily.
okay,
yourself.
but there is math that
Mhm.
tells us how to kind of go backwards from one transformation to the previous one.
Exactly.
For each,
We can do reverse for every
Axis
operation
that
in
we
the
are-
entire tree. For every single operation in the entire tree, we can encode it as one of these relationships. And so we know how it changes, how the children change in respect to the parent.
right,
If the children change, how will it impact the parent is really sort of what we're talking about. But since we're going backwards, it's, you end up talking about it in the reverse.
so we're on this manifold and we were started here and now we're, here.
Yeah, we're trying to,
Just
we took
down.
one step.
Right, we're down the hill a little bit to one side or
Yep.
whatever. Because you can do this math to run everything backwards, you can actually figure out which axes which levers had to get pushed or whatever to move us, not straight down.
We can
hill,
figure
but
out
down and a
When
little
I'm
bit to the
standing here
side.
on the hill, I can figure out which direction is down. That's all that the derivatives tell you which direction is down. You're literally, that's
Yeah.
why it's called a gradient in real life too. Physical
Uh-huh,
topology. It literally is a physical gradient. You're stepping down. So we know what basically, again, because we can tautologically say the output is 1 and everything is in proportion to that. Because really that's what that is. It's not a real derivative per se. It's a proportionate derivative. And we're saying there are relative derivatives all the way through this whole thing, which are all related to this output thing. And this output thing we're calling 1 because that's everything else is being defined in terms of the output, basically.
going through that process then, because the whole thing is how do I change this set of ones and zeros into the one I want?
Yep.
At the end.
No, you're trying to change the weights assigned to each node.
Right, but I mean, what transformation steps will be required to turn this input set of ones and zeros into.
But
it's not a
all the
network.
steps are the same. The only difference is the weights.
Yep, so the weights and which error they have.
Well,
are the
okay,
only two
so-
things that are
right.
different. So every different node has a different proportion of the blame, which we've been able to calculate recursively through the network backwards based off of this, declaring this as one proportion. So we know how good a job each one did, and we know which way to go to improve it. Because we know because it's a slope.
Right,
We know how to go down the hill. And so then we take each one of those nodes and we push them down the hill a little bit. Not too far. Again, if you push them too far down the hill, it can
Right.
jump over a gap or, you know, all kinds of bad.
so this year, we're gonna apply these 5, 10, whatever transformations every time. We
Yep.
run this whole thing. Those
So
are
what
those
we-
are the perceptrons.
So you want to know the full optimization, how it works?
Well, not
so-
quite, not quite.
Okay,
Sorry.
because you're talking about a lot of steps. I can tell you exactly.
Well,
It's really straightforward.
I
Let me just,
mean, but that's like, you know, I've got ones and zeros here.
Mhm.
I'm so putting them through these sieve
But you don't have ones and
layers.
zeros, right? You have like a whole slew of.
throw ones and zeros. If it's running a computer, it has to be ones and zeros. So
Oh.
he's right.
No, he's not.
He's right. For sure, it's ones and zeros.
He's not talking about the binary representation.
Are you
of
talking about the binary
floating point
representation?
number.
Well, actually, yeah,
Okay.
yeah, because that's, no,
You're like, oh, bullshit.
no, because ultimately everything is coded that way. And we,
There's no way to avoid it on a computer. You're putting numbers in boxes. That's all computers do.
Right.
All a computer do is put numbers in boxes. You can add and subtract
the
numbers.
only way this
you
can
can-
be automatic is if there's some sort of process by which we can convert that organization of ones and zeros to that.
That happens before the neural network. That happens between the transistor on the CPU and like the memory and everything. Like, that's not the,
Like the
No.
nodes still get a full number passed.
yeah, yeah.
Well, sure, but that's
Okay,
represented,
so how's the bind? Okay,
but that's represented by.
it's unclear how the bind. Yeah, everything's on a computer is represented in binary.
Right.
I 100% agree with you. There's no possible way to disagree with you about that. But the question is, how's that relevant to? That's what I'm just trying to figure out how that's.
It's not really,
Okay. all right,
because
gotcha.
the objection. was they're not
Okay,
really
gotcha.
ones and
Okay,
zeros.
so you were
It's
just
not really
addressing that.
important to what I'm saying that they're ones and zeros.
Okay, then keep
It
going.
just helps me to, because it is ultimately that.
He's technically
It's
right,
something.
even though it's meant to be floating point numbers, it's meant to be,
Whatever.
you know, but.
We got
but it
numbers
is
and
literally-
boxes over here. How do I get this arrangement of numbers and boxes to be that arrangement of numbers?
By changing each of the weights.
Right,
On every
so I
side.
know
So is
that
it
I'm gonna
all
put
like-
it through these 5 different transformations.
So the
Yep, each
Each
operation is
one,
like,
the only difference is that each time I'm gonna put a different weight into each transformation.
Yeah, so the neural network itself, the parameters that are
Right.
changing are the weights and the biases. And there can be other parameters in different neural networks, but let's just.
So I run it with these weights.
Yeah, you run it with these
I
weights.
get this arrangement.
I get
of
the error.
boxes. I compare it with what I want, through a loss function.
Mhm.
I do something involving the number 1. And that enable me to go back and say, okay,
I can't wait for people to give me shit about this
So,
forever.
the
Like, oh,
weight-
it should just-
the weights on
set it to
these
one of them.
5 filters
Mhm.
need to be shifted by this amount.
Yep.
I shift them and I do it all again. And I
That is-
keep doing
that is
that
it.
until I'm all the way at the bottom of
I
that.
just described gradient descent.
so is it all just trial and error? Is that how it, that's where
Well,
the error,
you-
the
but you know
error
which
comes
way-
from?
It's not,
That's
not.
the
ju- it's
error
not-
points the
yes, it
direction
is.
down?
It is trial and error,
Right.
but it's not purely trial and error. It's guided because we know which way is down. For every single parameter, we know if I move it this way, it's a good direction.
Right, and then
That's
the
how
error
it,
would
that's
say
how it
that
converges on a good.
it's not that way, so we know it's a different way.
Yeah.
And that's kind of how you calculate, then the loss function will say, there was this much error and we kind of knew the direction, but there was this amount of error, this amount, and that's like how you know how good, how functional it was.
Yeah, literally the whole thing that you need as a bare minimum requirement to be able to use a neural network is some way to measure did good or did bad and how good or bad did it do, which is
Uh-huh.
this loss function. As long as you can if you can shimmy something into a loss function, you can probably make a neural network I mean, neural networks are more applicable. They're better for some problems and worse than others.
So,
But
Oh.
yes,
go back to the, nodes with the arrows.
I never know which, this one or
Yeah,
this
yeah,
one. There's a lot.
that works, that works.
Okay, this one.
So each one of those arrows is a value.
Yep, it's a number. It's a scalar.
It's just, each one of those arrows is a scalar. So when you're going backwards, you're gonna hit here with your, whatever value it is that you pass back
Here.
in. But how do you split? How do you turn the output of this
Yeah.
into,
It's a very good question. That's what we're doing here. Okay, so how do we split it, right? So let's say we have an addition operation. Oh, oops, didn't mean to delete that. So let's say we have an addition operation here, right? We're not changing one gradient here, right? Because we have a parent node
Yeah.
and we got two child nodes,
Yeah.
right? We're changing the gradient of both of the children. Each of the children both has its gradient changed. Now, there's another question that's being begged for here. Someone else. Okay, the other thing is being begged for, the question is being begged to be answered, but is, but how do we deal with one node being the result of a whole bunch of different ones, right?
Right.
Because a neural network is
Right.
wired to everything is wired to everything else, right? That's how neural networks are, and that's why we add here. You see plus equals. We sum them.
So does it go backwards like exponentially?
It goes
Is it
backwards.
like on a family tree?
It goes backwards, but it's not necessarily, it's not
Not
necessarily,
exactly exponential.
it's not exponential, yeah.
But it goes
It's not
like
exponential.
with the blame game with the army, like the first
Exactly.
node back.
It actually gets less as you go down. the
Right,
middle,
right. But that first node, the one, or maybe not node, whatever that box was, is probably the most important. As you propagate backwards.
Yeah, I mean, I guess I don't,
Because
Sure,
that'd be the parent of all the other smaller ones
Yeah.
that go before it.
yeah, perhaps. I think that, yeah, I don't know. I think that, yeah, like sort of like the output layers, like on further closest to the output are
Uh-huh.
updated most frequently at the beginning. I guess I haven't really felt that much time thinking about that, but I think that sounds right though.
Yeah, because
makes
that's what
sense.
I was thinking with the
Yeah.
blame thing.
Yeah. So then I think that so then you're just saying that there's more error towards the output. And there's less, yeah, and I think that's the case, yeah.
Okay.
Basically. Although, I mean, if you literally were to perform the calculations mechanically, then you'd be able to tell for sure
Then
what it
you'd
looks
know
like. But most of the time you're not doing that. This is a thing that like a handful, not a lot of people on planet Earth know this, and everyone uses neural network stuff. This is just me going, this is me doing the Evan thing, which is I'm going to explain to you how it actually works instead of trying to just be like, oh, let's just use PyTorch. We could use PyTorch, but if you get this, you'll probably know more about neural networks than 90% of people that use neural networks.
So,
So it's worthwhile.
how do you choose the function, your node function? Your transformation?
Uh-huh. Again, these are sort of a priori mathematical things. There's sort of known mathematical rules,
Okay.
but again, that's what this program on the right here is specifically designed for you to be able to, you don't have to accept that there's a super smart mathematician guy somewhere who has figured out how addition works in terms of derivatives. You can just experimentally check yourself. And that's why whenever I'm unsure of something, I just take this and I'll just literally calculate it. And I'm just like, okay, that's what the derivative is here. So I'm going to go try to find an analytical solution on the internet. This is what I actually do. I compute it with this and I go on the internet. And I'm like, how do I compute the derivative for something? Right. And I go and try to find it. And maybe someone's done a better job because they're better at math than me. They're better at analysis than I am. So they've solved it. And I want to test to make sure it works. Then I can literally try taking that, plugging it in and see if I get the same value for the same inputs. And if I get the same value, then I know, oh yeah, that lines up. It checks out,
Are you saying though, like the perceptrons, like what I've been calling sieve layer, like how do you decide what
You're
those
seeing
are?
every function, right?
But
Addition
they're all
or
the same.
subtraction.
Well, so my understanding was that they were sort of like the cat pictures. You sort of one time take every third pixel and then the next time you take only the black pixels and the next, like they're sort of
Oh, so there's
almost random transformations of the data
Okay,
just to see if a pattern emerges kind of.
They're absolutely, okay, so I haven't, we've been chipping away at this, but, so the actual algorithm that you're using is called stochastic gradient descent. So now I'm pulling the bait and switching. Okay, so we were talking about gradient descent before, and I was talking about I said batch a couple times, right? But basically what a batch is, right, is we have our input output pairs, right? So I got our X1 through Xn, Y1 through Yn. Let's just say one input, one output to make it simple, right? So basically what I do is I take random pairs, random sets of pairs, and there's another hyperparameter called batch size, which is like the number of these pairs that I take at any given point in time. Because that you could, if you think about it, if I took all of the values at the same time and I had this gigantic data set, then we could produce really large gradients. And that's the biggest thing we're trying to avoid in neural networks a lot of times, is having too big of numbers in the network while we're trying to perform computations, because we get infinite or none and stuff like that. So basically batch sizes are really, it's kind of can be an important parameter in terms of like how you train the network. So then when you do a batch, you take all of our data sets, we take a whole bunch of random pairs, and then we take those out, and that's our batch we're training on then, and we compute the loss function with respect to all those pairs that we've, that
So are
match.
these, these are images or pixels?
I don't, anything you want. Whatever you want. This
However
works for
you've
any,
chosen to
it's just
model.
input output pairs. Let's say an input is some vector
Okay,
of any number of inputs,
okay.
but it's a fixed width vector and all of your samples have the same
Yeah.
fixed width vector. Same thing in your output. Any number of inputs, any number of outputs.
Yeah, okay.
Even though, again, at the very end, there's basically only one number, which is your loss function, which ends up being computed from the outputs of the network by usually, again, by subtracting it and, there's like a categorical loss function, which you use for if you're trying to do multi-labeling, if you're doing classification and you want to label, and there's possibly a whole bunch of different classes that a thing could fall in. It could be a cat, it could be a dog, it could be a bus, it could be a house.
So with the perceptron layers, those transformations, is that what you're talking about now? That those would be different in each of the batches? You would be applying different transformations to the data?
The input values, the X's here. These ones change. And when the X's change, then all of the W's change. So if I go back to this,
Yeah.
if I change the X's, then all of the Z's change, all the outputs of the activations change.
Oh.
All of the next Z's change, all the
What
outputs of these
right,
change.
right.
What
All
about
the
the
output of the whole
The
network.
app
What about the F?
It's all the same. It's one, think of it as one class. It's one function with different parameters.
Yeah, with the whole, the parameters have all changed.
I see.
Exactly. It's a function. Literally imagine you define a function, like he's saying, and you've got 80 billion inputs and one output.
Oh, so you're using all
That's
different
a
inputs
L.
to try and get that one output.
That's what this whole thing is, all just to get the output value so we can compare it to another one and determine how
Yeah.
good.
Well,
it
but
is.
putting
Right.
different weights,
Yes.
putting different weights into that one function.
Yep.
Is equivalent to,
Changing the function.
so like the cat picture again.
Mhm.
Maybe the function is, sample this one pixel.
Yeah.
Putting a different weight on it shifts which pixel we sample.
No,
No.
it changes the transformation. It changes.
Well, that's what I mean, but what
Okay, so,
you're
okay, every-
transforming is originally a bitmap.
Just to be clear, what's staying the same every time. Okay, so let's say I'm passing in, let's say, I don't know, I think MNIST images, I don't know if they're like 16 by 16 or 32 by 32, but let's just say 8 by 8 image, really
Sure.
tiny image. Okay, so we got this super tiny image. The upper left pixel maps to the same neuron for every single sample. There's
Okay,
N by N samples, which is the
Sure.
dimensions of the
Okay.
image. And it stays fixed every time. So we have one image, no, we have 1,000 images. And every single one of these images, we put it in, and that upper left-hand corner pixel it's always the same neuron gets the upper left-hand pixel. The same neuron gets the bottom right-hand one. The same neuron gets the center pixel.
But there's gotta. I feel like okay, no, that makes sense. So, yeah, that makes sense. Okay.
well, because each is a transformation on one input, and the input is what's in that box. Which is
The point is that
bit
all
value
of, the point is that all of the samples in your data set are supposed to be the same type of thing. So
Yeah.
you can't really mix it up by changing which neuron is pointing to which pixel. It's a fixed thing.
Uh-huh.
That part is for sure fixed. But the thing that changes is which image it is. And the idea that these are all the same types of images, or they all sort of, it's abstract,
Similar.
it's pretty abstract.
Yeah,
I'm not
well,
gonna.
I think my problem is that I have no idea how you would, like, what these actual algorithms are, like how you would take how even the machine, like if we're coming from a bitmap,
Okay, if you want to just
and we
talk
want a
straight
true
computer
or
science,
false.
I'm down to do that too.
I mean, if we have a bitmap,
I think that would,
we have a bitmap
That's
at
no
the
problem.
start, and at the
Okay, you
end,
want-
we have
do you want-
true or false.
Do you know
cat or
how we
mouse.
represent an image in memory?
Well, I mean, it can be a bitmap.
Yeah, no, all images, just so you know, almost every program that's manipulating images, it's a bitmap.
Right.
It's a bitmap 99% of the time.
It
And when you
may
write
be
it to a, when
stored
you
as
write
an
it to a file.
equation.
Right,
They
no, this is
compress it,
fine,
but-
right.
Yeah,
that's
yeah,
why
you write it
it's
to a
about the
file,
ones and
okay.
zeros, that's what I'm saying.
Okay, so the whole thing is ones and zeros. Okay, so how do we represent an image on disk? It literally
Right.
is, you can keep the channels separate. I used to work in machine vision, so I did this a bunch. Okay, so sometimes you have the channels be separate and sometimes the channels are together. But like, let's say the channels were together, and channels together means literally we have one, like, let's say we have floating point numbers. We're using 32-bit floats for our number. Even actually, no, let's say 32-bit integer. let's say 32-bit integer is 1 pixel, right? A pixel is 0 to 255, let's say.
Okay.
Okay, so we have a pixel 0 to 255, that's 32 bits, red value.
Yeah.
Green,
Right.
blue, even though it's actually often BGR, blue, green, red.
Sure.
But in terms of how it's put on disk,
Got it.
it's just a detail of the past, with how cameras used to
Got
work. So literally byte,
Right.
4 bytes, 4 bytes, 4 bytes,
Right.
and then we just have that chunk of 3, and we
Right.
just have that n
Right,
times. It's
exactly.
just a
It's
buffer.
a box of structs.
It's just it's a box of 3
Right.
4 bytes put together.
Right.
You have tuples of.
Right. So I got that, and then I've got that we're gonna take that and do different things to that
Yep.
table. And because we're doing it on multiple axes that.
You say table, it's not a table.
And
To be clear, it's all a straight
Well,
line of
yeah,
math.
I know,
Yes,
but-
that is,
okay,
okay,
but-
abstractly, it is a table.
and they're not actually different.
You're doing different things.
The
Yeah.
parameters are different.
Okay.
It's the same function.
Okay, so transform with different parameters.
Yeah.
Although, coming back to kerning, I mean, a function with one parameter changed
Mhm.
is a new function.
Absolutely.
It's a new output.
No, every single time you run the neural network, it's a different function
Right.
while you're training it,
Okay.
every single time. And once you're done training it, it doesn't
I
change.
think part of what I'm stuck on is that at the end, I'm still gonna have a big chunk of ones and zeros, not cat, true or false.
Okay.
I can't
yeah, yeah.
imagine any way to transform a bitmap
Yeah,
that
so-
results in true or false pattern.
Okay, well, the neural network is very good at figuring that out. For the record,
I
okay,
get
that's
that
it's,
top-
just to be clear, that's its job.
No, I know.
You're describing the black box that we don't understand. Just
Yeah,
to be
that's
clear.
So
So,
is there?
No, I guess you're just
Yeah,
asking,
okay.
what happens between the green and the purple?
Yeah,
okay, yeah, no, okay, no, we're between the green and the purple, okay, no, that's not necessarily matter. What he's asking is how does a cat that's like this, and it's all these pixels, how does that turn into a 1 or a 0?
But the output is.
That's what
not
you're
a-
asking,
The
right?
output is not a bitmap. The output is 1 or 0.
right.
Yeah, but are you not asking, how do you get from the green to the purple?
Well, pretty much. I mean, so I can
The
imagine.
green is the last layer. There's all
Yeah,
types
that's
of
the last
random,
layer.
there's
So you
just
have,
Yes, how does
freaking
it
random numbers in
consolidate?
there, as far as everyone's
yeah,
concerned.
what do you do? What do you do with all these outputs?
That's
Like, what
what,
You just add them up and call that the last function?
Yeah, there's some, generally speaking, you don't apply an activation function to the output. I
But
think,
you
but
have-
it depends on what exactly you're doing.
But you have to do something to combine all these numbers. You have to do some operator.
Yeah, so each one of these, this is what we're doing every time, except we omit the activation function possibly for the output. Although you could keep the activation function depending on what you're
So
doing.
you're adding, because you have the summation, yeah.
Yeah.
So what are
And
we
so-
supposed to not know? What's in the black box that that no one understands that we're not supposed to know?
That's the thing, I can't tell you that. There's no,
Right.
I'm not gonna be able to tell you that.
It-
The
what's
the
the
best
general-
scientist, the best.
it's the number,
general
it's the
process.
quantity, it's the volume of.
So, Okay,
Because you're dealing
what's
with-
this,
you're
okay,
dealing
this is the
with
way to think about it.
millions of these
And these,
equations. You're dealing with millions and millions,
And
an
the-
equation with millions of terms.
the
That's
black box is that we're able to change the weights. We're able to run this multiple times to adjust the weights and come up with something that makes sense.
That can get us 0.
Yeah,
But we
they can
don't-
get it, but we don't know
There's just so
why.
many.
It's just
I
dumb,
like it.
it's dumb hill climbing at scale.
I
All that it
like it.
was is
Yeah,
that
it's
when
just
you're,
like-
it's hill climbing at scale is all that it is.
But
And we
everybody-
do not know how it works on the inside. That's the secret, is
Yeah.
no one knows how it works. on the inside.
Why adjusting these?
I could give you a bunch of
It's
abstract
also like, if
explanations.
you get this one picture that's a field and your thing says it's a cat, you can't debug it. You can't, there's nowhere to go. Like, you
It's
have to
not
try
a
training
very
it over again.
debuggable thing.
No,
Very-
Like, that's why it's a black box.
Debugging
You
neural
can't-
networks is hard.
Yeah.
But here's a way to think about what we're doing with them, though. I guess the best explanation, someone said this a while back, it was the thing people were talking about a year or two ago, is looking at as like a really sophisticated compression algorithm.
Yeah, yeah.
And more or less what's in the network is a compressed version of your data that you're trying to mimic to some degree. It's a more abstract representation, so it's, and it can actually be better than, than like world-class compression algorithms, like, you take gzip on its maximum compression level, and you can make a neural network oftentimes be smaller than that. And that's literally what they do, in terms of you know, like what are embeddings for language models? I mean, we're not really covering language models today, but you know, embeddings are these abstract representations of things that you put in. Again, it's arbitrary. That's why it's hard to explain these things because they're always so arbitrary. What could be coming out of the output of the neural network? It could be whatever you want. It could be 0 or 1. It could be a floating point number. It all depends on you. Literally, it's all about being able to shape a problem the right way.
Mhm.
And then neural networks are good at solving the problems of that shape. So your job is just simply reshape the problem so that it's something that a neural network can do a good job on. And then its job is to figure out what try to solve for a black box function, and it can deal with, you know, nonlinearities and stuff like that. The way that, I mean, I guess another way that I think about it, and again, I'm just sort of riffing here, but another way you can think about it is it's sort of like warping the input space. Like you literally, what you can do is you can take at every node, you can go like, you can scan, right? So if we were to take our you know, our gradient here, right? So we literally take it and scan it. We could get this whole map, right? If we scan all the x1 and x2 here, right, our 2 dimensions, if we scan each of them, we could make this whole map or whatever, right? So if you want to understand kind of what a neural network is doing, and then more than just an intuition standpoint, what you can do is you can do this scanning at each of the output ones while it's doing a forward pass. Imagine if you had a graph of one of these at every single neuron, and it would show you the warped version of space that it sees. So you could literally plot, like, I mean, if you wanted to see how it warps it, I've even seen, that sounds really good.
So it's doing some kind of summation, like, you know, applying some operation to each of the things and then combining them to make a single result.
Yeah, update one or more results, but the end, actually, sorry, yes, the
And then-
output of the network itself is one or more results.
Right.
And then the final output, or the final like loss value, the total loss value, the cost value,
Right.
or there's different names for it. That total value is just one output. And that if that number, we want to make, you know,
That's what
we
0.
want to make number go down is all we
Right.
want to do is make number go down to 0. We want the number to be 0. And what it's good at figuring out is how to make the number go down to 0 if it fiddles with parameters and if those parameters allow it to change what's happening to the input values. That's basically,
TBD.
yeah.
I feel like we got a lot.
I'm not surprised that.
I
we-
feel like we covered a lot
No, it's okay. Yeah.
from the first hour.
I came in with optimistic expectations. You're all gonna learn now.